Yeah, thank you, Jonty. Okay, so as I told you, this meeting is happening partially because of this funding from the Medical Research Council. This funding is for analyzing bacterial infections in hospitals, antibiotic-resistant bacteria in hospital settings, and I would like to use the opportunity to tell you a bit about this research that I have been doing for the last 2 years with some collaborators, Theodore Caprayos at the University of Nottingham, Catherine Noakes at the School of Engineering at the University of Leeds, and Marco Felipe King in this same group. So let me give you a short overview of hospital-acquired infections, or they are also called nosocomial infections. So hospital-acquired infections are infections that you usually get in hospital facilities or in healthcare facilities. It is a very broad definition, so people use this both for viral and bacterial infections, and because it's a very broad definition, you have different ways in which hospital-acquired infections can be spread across individuals in a healthcare facility. So you can have a spread. Typical way of spreading is through contaminated hands of healthcare workers. So the healthcare worker here acts as a vector for the disease. It treats a patient. Maybe this patient is colonized with some bacteria, and by treating the patient becomes contaminated with the bacteria. And if the healthcare worker doesn't wash their hands following strict protocols and very well, it will treat a second patient and it will transmit the bacteria or the pathogen. There are of course some pathogens that are transmitted through the air, so you can also have airborne transmission in hospital settings. Contaminated clinical equipment can also act as vector for the disease, or contaminated surfaces. So you can have you can be colonized by some bacteria. You touch some surface, the handle of the door, the table, and then the second person that touches the surface can become contaminated with the bacteria. They can be especially problematic in these settings, as you can imagine. So there are opportunities for bacteria to infect open wounds. There are immunocompromised individuals in hospital settings. You have a lot of antibiotic use in hospital settings, so there is a link with antibiotic resistance in this area, in these settings. And then you also have some particular individuals in these settings, for example, healthcare workers, that can act as what we call super spreaders in the theory in mathematical epidemiology, because these are individuals that in short amounts of time contact many individuals, and so that they can spread the disease to many individuals in short periods of time. This is some data that I was getting yesterday from this paper. So especially problematic nosocomial infections are multi-drug resistant bacteria. In Europe, it has been estimated recently that 33,000 deaths per year occur because of multi-drug resistant bacteria. Around 75% of these are linked to hospital-acquired infections, so a huge problem that is becoming bigger every year. And that's why there are a number of control strategies that you can apply in order to avoid, normally it's in order to avoid the spread of infection in these settings. One way is, of course, to isolate infected patients. If you realize that you have an infected patient in a hospital ward, you can implement specific protocols to try to improve the hand hygiene levels of healthcare workers, so try to reduce the spread through the vector. Doing patient cohorting, you can do environmental cleaning of contaminated hospital wards. You can, of course, use antibiotics, decolonization procedures for colonized patients, and so on. Mathematical modeling. So mathematical modeling in this area has been going on for around 20, 30 years, mainly. There are many mathematical models that have been developed in this area. Normally, when you use a mathematical model in this area, is with two main objectives. The first one is to identify the most probable routes of the spread of the infection. So maybe you have some data for some particular outbreak in a particular hospital, and what you try to do with the modeling is to try to assess what are the most probable routes of infection for that pathogen, if you can guess that using the data and the mathematical modeling. And the second objective is related to those control strategies that I was telling you about. So something that you try to do with your mathematical model is to try to assess the efficacy of the control strategies. Which control strategies are working better in which situations? But when we develop mathematical models in this area, we need to take into account a couple of things. The first thing is that we are dealing with very small populations. So when you analyze an outbreak in a hospital, it is usually that you are dealing with a few dozens of patients, maybe if it is an intensive care unit, even if you include the number of healthcare workers. So it's a very small population. It's not that you're analyzing an epidemic in a city or in a country. It's something different. And the second characteristic is that these are highly heterogeneous populations. So we have populations where you have healthy individuals, in this case healthcare workers, for example, versus immunocompromised individuals all together. You have patients in different rooms. You have isolation of patients. You have airflow dynamics that affect differently different parts of the hospital. You have patient cohorting. So all of those things introduce a lot of heterogeneity in your population. So we are dealing here with a very small population that is highly heterogeneous. And if you have a very small population that is highly heterogeneous, normally what we teach our students and what you can see in textbooks is that you should follow a stochastic approach. We normally use deterministic approaches. We have seen here the use of ODEs to represent systems. Normally we use ODEs if you have a large population that is widely homogeneous. As soon as you start to have many heterogeneities or you have a population that is very small, maybe it makes much more sense to use a stochastic approach. So that's what I wanted to do when analyzing these infections, and that's what most of the people do in this area normally. Let me give you an overview of models that you can use to analyze these infections. So the first model is this one. This is like the most basic model that you can consider for hospital-acquired infections. This could be for a bacterial infection, for example, happening in a hospital. You have your patients in your hospital. Patients are classified in two states. They can be non-colonized or colonized by the bacteria. And then you make some assumptions about the events that can happen in your system. So you can have that a non-colonized patient becomes colonized. That can be due to cross-colonization. It can be due to endogenous colonization, or non-colonized patients or colonized patients can arrive or can be discharged from the hospital. And basically what you do when you develop a model in this area is to make a number of assumptions here about the rates at which these different events happen over time, or the probabilities at which these different events happen over time. But then, as I told you, there are, and then the stochastic process or your dynamics are given by patients moving from this compartment to this compartment, or maybe patients leaving the system or new patients arriving into the system. So the stochastic dynamics is just the movement of people across those two compartments through time with some randomness, if you're analyzing this from a stochastic point of view. And then there are some people that have tried to incorporate some heterogeneities into these processes. Some more complexity, no? Some more complexity into these processes. More complexity, for example, by considering the healthcare workers. As I was telling you, one potential way of a spread is through contaminated healthcare workers. So some people have included the healthcare workers into the picture. If you want, you can imagine this as those models that have been developed for malaria, in which in some models you only model the human population or the population of infected individuals, and in some models they incorporate the vector and they follow the population of mosquitoes and the interaction between those two populations. So this would be somehow similar. You include the vector and then you include your hypothesis about how a colonized patient contaminates a healthcare worker, how a contaminated healthcare worker can colonize a patient, and then also how a contaminated healthcare worker, by washing their hands, can become uncontaminated. And you still can have arrival and discharge of patients in the hospital, and you make, again, a number of assumptions about all your rates and all your probabilities in your process, how these events happen, at what rate these events happen. And then some people, so these models have been extensively analyzed from a deterministic and from a stochastic point of view, but then some people have tried to incorporate some extra complexity for the particular outbreaks that they were analyzing. So for example, there is this example by Wang et al., 2011. They were analyzing an outbreak in a hospital in Beijing, and in this hospital in Beijing, there was the particularity of having volunteers working in the hospital. So there were volunteers working in this hospital ward, and they wanted to incorporate the volunteers because they believed that volunteers were playing an important role in infection spread. If you want to incorporate volunteers, you have two options. One option would be to include the volunteers here as healthcare workers, and that would be it. You just increase the size of this compartment. A second option, well, the problem with this option is that if you believe that volunteers behave differently, if you believe that, for example, volunteers wash their hands less often, or you believe that volunteers have a different type of contact with patients, then you really need to include volunteers as a separate compartment. That's what they did. They had some assumptions about how often they wash their hands, how close is the contact between these individuals. And again, a number of rates and a number of assumptions. Normally what they do, and what these people did for this particular outbreak, is to use the data and maybe some Bayesian statistical analysis to calibrate some of the parameters in the model. Normally they want to try to calibrate this beta, these contact rates, which are the more difficult ones, and then maybe you make some assumption about the hand washing rate or the discharge rate. Maybe those ones you don't need to calibrate, but then the beta and the contact rates, you usually need to calibrate them from data. Some other people have been looking at other things. For example, Wolkowitz et al., they tried to incorporate environmental contamination. So what is the role played by surfaces contaminated in the hospital ward? If you want to include environmental contamination, one way of doing this, is not the only way, but one way of doing this, the way that they followed, was to include surfaces as agents in your model, as individuals. So I have a number of surfaces in this hospital ward. I make a list of the surfaces that I belong are playing a role in the infection spread, and now I incorporate those surfaces into the picture, and now I also have random movement of surfaces from uncontaminated to contaminated. And I also have some cleaning rate at which surfaces become uncontaminated again. And again, I make some assumptions about the touching rate from patients or from healthcare workers to surfaces and so on. They did this for an outbreak of a bacteria in a hospital in Germany, in a hospital ward in Germany. And again, they did some Bayesian statistics to calibrate some of the parameters in this model. And once you have calibrated the parameters, you can start to play around and see how control strategies could help to decrease the infection spread. No, that's what they did. Some other people have been trying to incorporate spatial components. That was myself some years ago. So I wanted to show how you could try to incorporate, for example, the spatial characteristic of your hospital ward. So for example, you could imagine that patients in the same room have a different infection rate than patients in different rooms. And if you want to do that, then what you need to do is to take this compartment for patients and split the compartment for the different parts of your ward or the different spaces, not the different rooms. So that's an example here. Another example of incorporating, so potentially you could try to represent here that if a healthcare worker is treating patients in the same room, then because the healthcare worker is a vector, they are sharing the same healthcare worker, so they should have a larger transmission rate. If you really want to include the contact network structure between healthcare workers and patients, and you really want to do that, something like this could work. The model by Laura Tommme in Institut Pasteur and Lula Opatowski. So they tried to model the spread of a bacterial infection happening on this hospital ward, and for this hospital ward they had a number of patients and then different types of healthcare workers. So you have these pink ones, the blue ones, and the green one. They represented in this ward 3 different types of healthcare workers. I believe these were nurses, doctors, and a radiologist. And then they believe that if the transmission is happening through the healthcare workers, you should analyze the epidemic happening on this contact network. So that this guy cannot infect this guy can only infect this guy or this one here. And then you could analyze the epidemic happening on this network. So as you can see, many different approaches to this problem. This is another example. This is Catherine Knox from Leeds. So they propose a methodology to analyze nosocomial infections using airflow dynamics. So trying to incorporate the airborne transmission into the picture. If you believe that you are dealing with a pathogen that is transmitted through the air, something that you can do is to try to include the airflow dynamics into your epidemic model. And they did that, I will refer to this later, but they did that by considering, for example, this hospital ward. In this hospital ward, you have patients in the different rooms or the different bays. These bays are joined through this corridor, and imagine that you have some information about how the air flows in this hospital. So if you have that information, you can try to incorporate the information about the airflow dynamics into the epidemic dynamics. I will talk about this later, but just another model of spread of pathogens in hospital settings. So as you can see, there is a huge amount of models. I didn't present of course, all of them. Huge amount of models in the literature to analyze these kind of pathogens. And when I was reading at all of these papers, I was thinking that it would be nice to have somehow a general model that captures all of these models as particular cases. So if you can create a general model, a very general model, that has all of these models as particular cases, and then you do some analysis to this general model, the analysis applies directly to all your particular scenarios. And it happens that it is possible to do that because all of these models at some point have all the same shape. In particular, this is the shape. So this is a very, very general model for hospital-acquired infections, and I'm going to explain to you the model in a very abstract way because it's a very abstract model. So it's a multi-compartment SIS model. So you have individuals in different compartments. You could understand this as different types of individuals. Could be patients, healthcare workers, surfaces, volunteers, patients in different rooms, patients in different parts of your network, whatever. So different types of individuals. Individuals can be in two states, susceptible or infective, non-colonized or colonized, and contaminated or contaminated. So again, very general definition of the susceptible compartment and the infective compartment. And then very general rates at which these guys, these people, move from one compartment to the other. So those movements happen with some rates, mu and lambda, that are general functions of the state of your system. The state of your system is how many individuals you have in each compartment over time. I'm making here an assumption, which is that the number of individuals in each level is constant, so you don't need to follow the susceptibles if you already know how many infectives you have. So the state of your system is this vector that tells you how many infectives you have in compartment 1, in compartment 2, in compartment M. Capital M is also a parameter in this model, so I can choose the number of compartments in my model, that's capital M. And then lambda M and mu M are just general functions that you could define. I also included here detection of the outbreak. That's because some of the models in the literature include screening policies, ways in which you detect that you have an infective individual, maybe the time until the individual shows symptoms or whatever. So you can also incorporate, if you want, a rate at which you detect that you have an outbreak. If you are not interested about that, if you don't have detection in your model, you just set up this parameter equal to 0, this function equal to 0, so this part of the model disappears, and then you analyze this other situation where you don't have a detection. This is a stochastic process, so this is going to be a Markov chain. Your Markov chain is the number of infective individuals in each compartment over time. It's a Markov chain because you make the typical assumption when you're analyzing this from a stochastic point of view, which is that the events happen after exponentially distributed random times. So everything is memoryless, everything is Markovian, and you get a Markov chain. That's the usual assumption when you do Gillespie simulations for chemical reactions and all of that. And then the reactions here in your process, or the events, are a colonization of a patient or an infection of an individual in group J. So in group J, you get one more infective at some point. That's an infection happening in that compartment. You can also have a recovery, and recovery means here something very general again. Could be a decontamination of a healthcare worker, it could be a decolonization of a patient, or whatever. So in compartment J, you lose one individual with rate mu, and then you could also have detection if you have detection into your model, if you have some screening policy, or you have your individuals showing symptoms after some time, or whatever. So very general model, and what I would like to try to convince you about is that this model has all the previous models that I have shown as particular cases. So basically what you need to do is you choose capital M, depending on the model that you want to represent, or the data that you are dealing with, or the outbreak that you are dealing with. You choose wisely those functions, lambda, mu, and delta, and then you can reproduce exactly all the dynamics from all of those previous models that I presented before. For example, this one, I would choose capital M equal to 1, lambda, mu, and delta in this way, and by choosing lambda, mu, and delta in this rate, these hypotheses that I had here are exactly represented. so that exactly the same dynamics are obtained. So it's not a different model, it's the same model with the same stochastic process with the same dynamics. It's just a different way of representing the same. But now my model also works for the others, so I can choose m equal to 2, and now these would be patients, these would be healthcare workers, these are my rates, and these rates have been chosen so that I can incorporate the hypotheses that were originally proposed in this paper by these people. And then also here, I have here 3 compartments because I also have volunteers, and all the hypotheses that I had originally here are given in these functions, lambda, mu, and delta. Also here, of course, instead of volunteers, you can have surfaces, but it's the same. Here as well, because here, if you want to analyze the epidemic dynamics happening here, basically what you need to do, as I told you, is to split the patient's compartment into 4 areas, 4 compartments, which could be how many colonized patients you have in room 1, in room 2, in room 3, and in room 4. So I'm going to get 4 compartments here, and I can analyze how patients in the different rooms become infected and how they recover or they are discharged from the hospital. So again, I can get these same dynamics by using this framework here. Even the network, so even the network, you can do that. This is a bit more, I mean, this is funny somehow, because when we think about an epidemic happening on a network, we think that that's the contrary of analyzing a compartmental-based epidemic model. But in fact, an epidemic happening on a network is an epidemic happening in compartments where the number of compartments is equal to the number of individuals. Basically, an epidemic happening on a network is a compartmental-based epidemic model with 1 individual per compartment. So everyone is different, so you just have 1 individual in each compartment, and that individual can be susceptible or infective. We can do better than that, because if you have a network like this one, there are some individuals that can be grouped together in the same compartment. And that's because some networks have some symmetries, and you can use the symmetries of the network to reduce the number of compartments. That's something that has been shown with all the technicalities about how to do that in an algorithmic way. Istvan Keys, Peter Simon in the UK, they have been showing how to do that. But an easy way of understanding this is that, for example, if you look at this network, these 2 patients are actually the same patient. They are exactly the same. They are completely symmetric. In this epidemic, these 2 patients are treated by the same people. So in this epidemic, you don't really need to know who is infected here. You only need to know how many of these 2 are infected. And when you start to think about how many, it's because you have a compartment. So in fact, those 2 guys could be put together in the same compartment so that at the end you get 11 compartments, even if you have 15 or 16 individuals. The more symmetries that you have in the network, the better that you can do, the more that you can reduce the number of compartments. I didn't explain it here in this paper, but in fact, there are more symmetries that you can exploit in this network to reduce even more the number of compartments. For example, in this network, the top part is symmetric to the bottom part. If you use that symmetry, you can even reduce more the number of compartments, so it is well known how to do that. But the idea is that this network epidemic model for this hospital can be also represented in terms of a compartmental, in terms of this unified framework. You will just need to define these lambda rates and these mu rates so that you can accommodate the hypothesis in this original paper. Just to say that if you're interested about epidemics on networks, we have these results in which we analyze we explain how to analyze the SIS and the SIR epidemic models for very, very general networks. So this could also be used in this setting if you want. And then the airflow, the airborne transmission model can also be represented into this framework. This was surprising. I hadn't realized about this, but then when I came across with this paper, I just realized that the way in which they had modeled this epidemic happening in this hospital could actually be represented also in this framework, where basically your infection rates, lambda, need to be defined so that you incorporate the airflow dynamics. And it can be done so that these airflow dynamics are incorporated into these infection rates here. So again, this can also be represented in this unified framework. So now we have this very general framework. How is this useful? Why is it useful to have a general model that has all of these models as particular cases? One good thing about this is that, as I said, is that if you do some analysis now, here, that analysis is going to apply directly to all the models at the same time. What kind of analysis can you do? There is this nice paper by Matt Killing and Joshua Ross, where they basically explain that when you analyze epidemic processes, one way of analyzing an epidemic process, of course, from a stochastic point of view, is to analyze the Kolmogorov equations. So you have your Kolmogorov equations. In chemical reaction theory, it's called the master equation. It's the same. It's a system of ODEs that gives you the transient probabilities of your Markov chain, the probability that your stochastic process at any given time is at any given state. Those probabilities satisfy a system of differential equations. That's the Kolmogorov system of differential equations, or the master equation. The problem with that is that the solution is not trivial. Normally, you cannot solve that system of differential equations, so that's not very helpful. There is a theoretical solution in terms of the exponential of a matrix, not very helpful because it's difficult to compute the exponential of a matrix. So what they try to explain here is that sometimes you don't need to do that. Of course, another option would be to do simulations, but they were trying to look for something in between. So can we do better than simulations, even if you cannot deal with the Kolmogorov system of differential equations? And what they explain in this paper is that there are many things about an epidemic that you can analyze without looking at the Kolmogorov system of differential equations. You can look at the epidemic size, for example, how many people will get infected in the population during the outbreak. You can look at the length of the epidemic, for how long the epidemic lasts in the population. You can look at other things, cost functions related to the outbreak. You can look, of course, at the reproduction number. That's something that we do all the time in mathematical epidemiology. We don't look at the Kolmogorov system. We don't look at transient probabilities. We just try to compute the reproduction number. The reproduction number is basically similar to these things. It's just a summary statistic. It's a number that gives you some information about the outbreak. So in this paper, they explain how you can compute different summary statistics for your epidemic. So that's what we tried to do. We are going to focus on the reproduction number. So that's what we are going to be interested in, because it's normally what people look at, and because this reproduction number is going to help us with the first objective that I was talking about, which is assessing which routes of the spread are more important in your epidemic. What are the routes of infection in this hospital? The reproduction number. So we are going to define the reproduction number more generally than how is usually defined in the theory of mathematical epidemiology. The reproduction number, as, for example, Citabra explained the other day, is the average number of infections that a single infective individual causes until the individual is removed in a fully susceptible population. That's the general definition of the reproduction number. But if you are thinking about a stochastic process, and you think about when you do simulations and you get a single infective individual, and this individual infects some people, the number of infections is a random variable. So this guy will infect one person, 2 people, 3 people, 4 people with different probabilities in your simulation. That is telling you that that number is a random variable. It's not a number, it's a random variable. And if it is a random variable, why would I focus on the mean if I can compute, for example, the distribution? So instead of defining the reproduction number as an average, I will define the reproduction number as a random variable, and then if I want, I can compute the mean, or the variance, or the whole distribution. So that's the definition that we have here, number of infections. But now I have different types of individual in the model. So in the model, I have all these different types of infective individuals. So each of these infective individuals are going to have different reproduction numbers. So what I can do is to define the reproduction number for each type of individual. That's Rj. Rj is the reproduction number, or the number of infections caused by an infective individual located at compartment J, so individual of type J, patient, healthcare worker, a surface, whatever, until the individual is removed. That depends on your model. It could be detection of the individual, it could be the end of the outbreak, it could be the individual is discharged until the individual is removed in your system. Recovery. I can do even better, because that reproduction number is going to tell me if I have this individual in group J, how many individuals this individual infects. But now, these infections are happening across different types of individuals as well, because this individual here is going to infect people here, and here, and here, and so on, depending on my infection rates, lambda. So I can actually define Rj as the sum of Rjk for different values of k, where Rjk is the number of infections caused by an infective individual located at compartment J among individuals at compartment K. This is going to be helpful, and this is going to be helpful because if I am able to compute this number, or the distribution of this random variable, or the mean, or whatever, that is going to start to tell me the routes of infection. It's going to tell me if this individual is dangerous because he's infecting people in this compartment or in this other compartment or so on. So now this reproduction number help with this first objective of analyzing the routes of infection in your epidemic. Now, what can we do with these reproduction numbers? As I told you, it's a random variable, so ideally I would like to compute the distribution of the random variable. The distribution of the random variable are these probabilities. For example, if you focus on Rj, instead of Rjk, Rj, the methodology is the same. You want to compute the probability of your reproduction number being equal to n for different values of n. You could infect 0 people, 1 person, 2 people, or so on. Of course, this depends on the initial state of your epidemic. So normally, when we define the reproduction number, we assume a fully susceptible population. But you could do this more generally, and you could analyze your reproduction number for any initial state of your epidemic. And then if you want, you can particularize this initial state so that you have a fully susceptible population around the infective individual. But we can do this more generally. So in fact, this quantity now depends on J, the initial state, and the number of n, okay, the number n. Now, I'm not going to enter into the details of this, but it is possible to compute these probabilities, okay? And it is possible to compute these probabilities by following something that is known in Markov chain theory, which is a first step argument. Basically, what you do is you think about if your system is in this state at the beginning, what is the next state of the system after one event? If you think about that and you make that argument, you get a system of equations where now these quantities depend on the initial state and depend on each other. And then what you get is a system of equations. And if you solve this system of equations, and this is not a system of differential equations, this is a system of linear equations, you get the solution of your probabilities. So you get the whole distribution. You can do this for any value of n, so you can get the solution of this. This is not very widely used in mathematical epidemiology, and it's because the number of equations that you get grows with the number of states in your Markov chain. Basically, the number of equations that you get is as large as the number of states in your Markov chain, your stochastic process. So what are the possible states of your system at any time? And that number is huge if you have huge populations. In particular, this number is this quantity here, which grows with the number of individuals in each compartment and with the number of compartments. So the more heterogeneous that is your population, the worse this gets, and the larger that is your population, the worse that this gets. The good thing about this is that I told you that in hospital-acquired infections, we have small populations. So even if you get a very highly heterogeneous population, because these numbers are usually low, I have seen that normally when you play around with the numbers that people are looking at in these models, you can actually solve these systems easily. So you solve this system, you get your solution, you get the distribution of the reproduction number, and then if you want, you can get the mean or the variance or whatever. There are efficient ways, of course, of solving this system. It's a sparse system of equations. There are very efficient methods for doing this. Some results, I'm going to skip a bit of this, but just to give you a flavor of the type of results that you can get. Imagine that, for example, you have this model. This was the original model by Wolkowitz et al. They were looking at environmental contamination. They had the surfaces here. So you have three populations here. You have your patients, your healthcare workers, and your surfaces. And now, thanks to this technique, you can start to look at reproduction number of a patient, reproduction number of a healthcare worker, or reproduction number of a surface. So what you can do is, for example, for a patient, what is the reproduction number of this patient among healthcare workers? This is telling you, during the infectious period of this patient, maybe until the patient is discharged from the hospital or until the patient recovers or whatever, depending again on the pathogen and everything, this individual is going to contaminate a number of healthcare workers. So I want to know that distribution, that number. Here I'm just plotting the mean, but you could compute the whole distribution. Actually, I was computing here the whole distribution. So this heat map shows with the color, this color is the reproduction number, the number of healthcare workers that the person contaminates. These are two parameters in the model. The blue dot is the parameter values that were proposed in this original model. So after the calibration, after they calibrated this model with data for this hospital in Germany, they got some parameter values. So I'm not doing any calibration here. I'm just taking the values that they got. And with their values, I'm computing here the reproduction number. And now is when you can start to play around and think about control strategies. So what happens if I decrease the length of stay, if I increase the length of stay, if I try to reduce the contact rate between patients and healthcare workers, and so on. So now this type of plots are showing me the importance of each route of infection, but it's also helping me to assess the efficacy of different control strategies. You can also think about the reproduction number of a patient among surfaces. So a colonized patient, how many surfaces contaminates until the patient is removed. But you can start to think also about the reproduction number of a healthcare worker, the reproduction number of a surface, and so on. So a contaminated surface, how many patients colonizes for these parameter values, or when I vary the parameter values. For example, when I vary the surface decontamination rate. Good, so this is just an example of the type of results that you can get. I wanted to use this final minutes to tell you a bit about this idea of incorporating airflow dynamics. So if you're analyzing a pathogen that spreads through the air, can we try to incorporate into the model how the air flows in the hospital ward? There was this original idea by Catherine Knox and Andy Slake. They basically proposed how to do that by linking an epidemic model with an zonal ventilation model, what is called in indoor air, in the indoor air research area. So they are engineers, they do all of this stuff. So they basically model the movement of air in these indoor settings. And you can try to link that with the epidemic dynamics. So imagine that you have this hospital ward here. This was just something that they made up, a very simple hospital ward with 3 bays. And now you have these 3 bays connected with this corridor here. What they do is they split the ward in different compartments, in different spatial compartments. They just discretize the space. They discretize this space in 9 different areas, or what they call ventilation zones, so 9 ventilation zones. In this base, you are going to have patients, so your patients are located in these rooms here. I think we are assuming here six patients per bay. And now we have these 9 ventilation zones, 3 ventilation zones for the corridor and 6 ventilation zones for your base. I'm going to have this epidemic modeling happening. This epidemic model is the previous one, is the unified one, so you can use the previous techniques if you want. So this is just patients that can be non-colonized or colonized with whatever pathogen that you are analyzing, or infective with whatever pathogen that you are analyzing that is spread through the air. And then they propose this zonal ventilation model for the spread, for the contamination of the air in this hospital ward through time. So basically they have these variables here, which are the concentration of pathogen at zone I at time t. This is a deterministic model for the spread of pathogen, and they propose this system of ODEs for how this concentration of pathogen varies through time in each area. Now, how are these ODEs designed? So this concentration of pathogen is going to increase because infective individuals are producing pathogen by breathing. So that's this contribution here, where this is the number of infective individuals in zone I. This is also going to depend on time, that I, so I will talk about this later. This is an extract ventilation rate, so this is how much air you are extracting from one room due to your ventilation system. And this is movement of air due to your ventilation system across the different parts of your hospital. Those are these beta rates. These beta rates is just rates that they try to estimate from indoor settings about how the air is moving across the different zones. So this is telling you how the concentration of pathogen evolves through time. I have these rates here, these parameter values, but now I have the problem that this concentration of pathogen changes through time, but the number of infective individuals also changes through time. And the idea, or the main hypothesis that we are going to make here, is that the rate of infection, this rate of infection of susceptible individuals in any given area is proportional to the pathogen concentration in the air in that area. And if you make that hypothesis, you can try to use this equation to get these infection rates, lambda. Now, how do you do that? The way that they proposed to do that, so they originally proposed this model, and then I have been working with them to try to improve it and try to do some more things. So the way that they originally proposed this was to consider that these things are happening at two different time scales. So movement of air is happening in the order of minutes, 1 hour, 2 hours, and then infections are happening in the order of many hours or maybe 1 day or half a day. So because that's like that, you could make an assumption which is, I'm going to run my epidemic happening in this hospital ward. Maybe I start with one infective individual in this hospital ward. This infective individual is breathing and is producing pathogen, so I have this contribution here. And what I'm going to do is, I'm going to compute a steady state values for this concentration of pathogen in the air. With that steady state value, I'm going to compute my infection rate for each individual in this part of the world with this hypothesis about being proportional to the amount of pathogen in the air. With those infection rates, I can run my simulation or my epidemic until some individual gets infected, for example. And when another individual gets infected, I come back here, I recompute the steady state values of my concentration of pathogen. With those values, I compute my new infection rates and so on. So you could proceed in this way, and in that way you are trying to link those two processes happening. That's how they did it. They did these simulations, but then what I realized is that in fact, if you are doing that, what you are doing is proposing a particular function, lambda. Your function lambda comes as the solution of this system of ODEs. So if you compute the steady state value of this system of ODEs, that of course depends on the number of infective individuals, but that's fine because lambda depends on the number of infective individuals. Now this lambda function is just proportional to the solution, the steady state of this system of ODEs. And that's why the proposal for the lambda rates have this shape here. So this shape here is that the lambda rate for individuals in zone 1 depend on how many infective individuals I have in each zone, and they depend in a very funny way where you have P is the pulmonary rate, is how much you breathe per second, Q is the quanta parameter, that's more or less telling you how much pathogen you produce per second. This is the number of infective individuals in each zone, but then in this matrix V, you have all your airflow rates. And now somehow, every ventilation regime or different ventilation setting that you have would have different rates, Q rates and beta rates, and would have a different matrix V. So every time that you change the matrix V, you are changing the ventilation setting in your hospital. All right, so almost finished. Now, this is the type of numerical results that you can get. We were looking at, in this imaginary hospital ward, we were looking at different possible ventilation settings. So we proposed 6 different ventilation settings that could be realistic. Again, like they are the experts in doing this. They have these collaborations with hospitals. They try to measure airflow dynamics happening in hospitals. So they propose some plausible parameter values for the airflow. These would be beta rates going from one room to the other and the other way around. The circle values would be the extract ventilation in each zone. Remember that we have 6 individuals in each bay, so 3 individuals per zone. And then for these settings, you can compute whatever summary statistic that you want. Instead of reproduction numbers, here reproduction numbers wouldn't make much sense because individuals don't get infected due to contact, they get infected due to breathing pathogen from the air. But you can propose a different summary statistic. For example, we were proposing this summary statistic, which is the number of infections in the ward until detection of the outbreak. If you imagine that you have some screening policy or individuals are showing symptoms, you can imagine to compute how many people are going to get infected until you realize that you have an outbreak, and how the ventilation setting helps with decreasing this number, or can help with decreasing this number. Again, a system of linear equations. You solve this system of linear equations, you get your solutions. It's possible to do that. Exact solutions, these are not simulations, exact solutions, exact probabilities. And this is the type of results that you can get. So here, this is the number of infections being equal to n versus n. That's the distribution. The colors are the different ventilation settings. The red star indicates the best distribution, so the best ventilation setting, the ventilation setting with the smallest number of infections. The dark points represent the worst ventilation settings. So basically, this is just to show you that you can try to identify which ventilation settings are better in which situations. And then you can also think about what is more important. Is it more important the ventilation setting that you have, or is it maybe more important the screening policy that you have? Is it more important to detect the outbreak soon enough, or is it more important to have a good ventilation setting? So we tested different hypotheses about the average time to detect the outbreak and how these distributions change. One of the things that we found, and this is a toy model, it's a very simple model, it's the first time that this has been done in this way, with this methodology. So the first thing that we saw is that detection dominates ventilation. So it seems that detection is much more important than ventilation. Also, ventilation also has an impact. The second thing that we saw is that, for example, of course, ventilation settings, you cannot say one ventilation setting is better than the others because it depends on where your initial infective individual is located in the ward. But still, you can identify some ventilation settings that seem to be bad regardless of where the individual is located at the beginning. So still you can identify good ones and bad ones, or at least some of them that are not so good. And something funny or something interesting that we found is that sometimes when you tweak your ventilation setting, when you change the airflow rates, you can decrease the number of infections in the hospital ward, but maybe the price that you pay is that you increase the number of infections in particular areas of the hospital ward. So if you split the number of infections as the sum of infections in room 1, in room 2, and in room 3, now by switching from one ventilation regime to another, you might be able to go down in the number of infections, but you are doing exactly the contrary in a particular area. So you need to be taking this into account because then, I mean, this has some issues, of course. So this was interesting to find. And with that, I think I'm going to finish. I would like to finish thanking all my collaborators in these projects, but also in related projects. Many of them are here. With Antonio, I have been working also in epidemics, also for hospitals, Carmen and Grant, and Jonty, who is here. So we have been working at more modeling within host infection dynamics. Suma and Narmada, who is going to be talking after me, and Sarthak, who is going to be presenting a poster also about epidemic modeling in a different area, and some other collaborators, Joshua Ross, Anton Camacho, and so on. I would like to thank also the Medical Research Council for the generous support through this fellowship. And if you are more interested about the details, the technical details, you can find those in this paper with Theodore Caprayos and this paper with Catherine Knox and Marco Felipe King. And now if you have questions, I'm happy to take them. Thank you very much.